Hello to our friends joining us via recording. We are doing our second session here on lesson number 9, which is about the way that the muscular system works. Before we start talking about the way that the system works, we need to remind ourselves of some of the important words that we're going to see coming up a lot during our class time today. So these words are listed over on the right side of the screen here. These are special words that are only used to describe muscle tissue. We work together with groups of classmates to match these terms up. So for all my friends here in class, do me a favor. Up above the pointer, you've got that pencil. Go ahead and click on the pencil. Let's work on drawing some lines to connect my descriptions here to my terminology that we see over here. Let's match up those words together. Perfect. Is it just me, or do the colors and the way that our lines are drawn, does it remind anyone else of in Star Wars when Palpatine's like sending out his lightning rays? Like they're not lightning. I'm not good enough at Star Wars to make a reference like that, but it totally, when you guys started drawing that, I was like, oh my gosh, like we're electrocuting our words here. So I'm glad I'm not the only one that feels that way. Okay, so let's briefly run through our terminology, because we're going to be using this repeatedly today as we fry each other, right? Exactly. Yes, Hannah. I am the Senate. Exactly. My husband will appreciate that I made that reference in class today, so I'll have to tell him. He'll like that. Okay, our first term that we electrocuted today was muscle fiber. When we talk about a muscle fiber, what I'm technically referring to is a muscle cell. So you will hear that terminology a lot today. Muscle fibers contract. That means that a muscle cell is contracting. The sarcoplasmic reticulum is going to be really important today as we start talking about muscle contraction. The sarcoplasmic reticulum is a muscle fibers version of the smooth endoplasmic reticulum. Do we remember from lab or from our working here in lesson number 9, what does the smooth ER store? What's there a bunch of inside the smooth endoplasmic reticulum? Do we know? Yeah, so Gloria was questioning it, but she was right. Nicole's right too. The sarcoplasmic reticulum, what you must know about it is that this is where a muscle fiber stores its calcium. We only release calcium when we want to do muscle contraction, so I need a place to store it. This is the place inside a muscle cell that I store it, the sarcoplasmic reticulum. When I talk about the plasma membrane of a muscle cell, I call that the sarcolemma. Now, there's a term that didn't make my list here, but it is another term worth us knowing as we're getting ready to start talking about muscle contraction. And that term, let me add it to my list, are things called T-tubules. T-tubules. Does anyone remember why I'm putting this term T-tubules by the sarcolemma? Do we remember what T-tubules were? I only talked about them briefly during lab, I think. Carol, let's see if that I've figured out how to get that emoji when I type it. We don't remember. Okay, actually we do remember. That's a lie. Dr. Ellis doesn't wait long enough. I need more coffee, because then I'd be drinking my coffee waiting for you guys to answer. So nice work. 3 of you totally squashed my cricket, which is good. When we talk about these things called the T-tubules, they are places where I fold in the sarcolemma. When a muscle fiber is contracting, I want my entire cell to contract, not just the parts that are really close to the sarcolemma on the outside. So the way that I can get my entire muscle cell to contract is to fold in the sarcolemma into shapes that almost kind of look like those honeycomb cereals, fold it in the middle, so that more of my proteins are close to the membrane. So those places I folded is called T-tubules. And yeah, Nicole, you're right too. By having T-tubules, the surface area of my muscle fiber is bigger because it's just places where I make the plasma membrane. I extend it into the cell. So it's not just on the outside, now it's on the inside too. And that's going to be important because the way that muscle contraction happens is I change the charge on the sarcolemma. So I take it, here we got slightly different numbers today. We hate it when we have to do numbers, right? But the slightly different number, my resting membrane potential, which is my normal charge on the sarcolemma, my normal charge on the sarcolemma is negative 90 millivolts. When it's time for a muscle cell to contract, just like with those neurons, I make this go positive. But so the way that a muscle contracts is I have to take this charge, negative 90, and make it positive. I make it positive by interacting with my environment. So if I fold my plasma membrane into these things called T-tubules, that's going to allow me to change the charge everywhere. So it increases surface area. It makes it easier for me to send that message across the membrane. Last thing left that we have here is what's called the sarcoplasm. So the sarcoplasm is the cytoplasm of a muscle fiber. Remember that the terminology, let me type it over here, cytoplasm. When we talk about the cytoplasm, that's made of two things, right? We've got the cytosol, that's our soupy stuff, and then all of the organelles that are inside of it. So the sarcoplasm is the cytoplasm. It's the soup, and it's the organelles that are on the inside. All right, so there's some of our important terms. We reviewed our terms. Now let's move on to talking about our channels. Gotta love those channels. The channels that we are talking about in today's lesson are gated channels. So remind me in the chat, gated channels always or not always open? Gated channels always or not always? Yeah, not always open. That's what gated means, right? Gated means they have a gate. I gotta get that gate open. Hey, do you guys remember what's the name of the type of channel that are always open? Move stuff really slowly. What's the ones that are always open? Yeah, exactly. Leakage channels are always open. Absolutely. We're not going to care about leakage channels today when we're talking about muscle fibers. We're only going to care about gated channels. And we're going to care about each of these kinds of gated channels. So let's do these three questions. Which of these types of gated channels opens up when I push on it? Which kind of channel opens when I push it? Yeah, the one with the really long name, right? So what opens a mechanically gated channel is when it's pushed or when something physically changes its shape. This is kind of your normal gate that you might have on your backyard. You push it open. A mechanically gated channel, got to be pushed open. Hey, when I talk about a voltage gated channel, what opens up a voltage gated channel? How do these ones get open? Yeah, so that voltage word refers to charge. So the way that I open a voltage gated channel is I change the membrane charge. If I take my membrane from being positive and I turn it negative, or if I take it from negative and I turn it positive, that's going to change whether or not these voltage gated channels are open. So the last kind that's left here then, those chemically gated channels. What opens a chemically gated channel? Chemically gated. Yeah, exactly. I think that Gloria knew what question was coming next, right? Because she had a nice long answer for us there. Chemically gated channels open with a chemical key. Chemical key. So think about it like a lock. I use a chemical that's acting like my key to unlock that gate. Whether we are talking about gated channels or leakage channels, both of these types of channels transport things the same way. Which way is it? Is it up or down when we talk about transporting through channels? Up or down the concentration gradient? What do we think? Okay, so it was up for debate in our groups, right? These types of channels do move things down their concentration gradient, so down the gradient. The way I know that is because gated channel proteins or leakage channel proteins, they do passive transport. What does passive transport mean? What is passive transport? All of our least favorite topics from unit number 1, right? They're all coming back to haunt us. Exactly. So passive transport means I don't need any energy. The way to make passive transport happen is I go from high concentration to low concentration. I go from high to low. If we're going from something that's up high to something that's down low, we're going down the concentration gradient. So keep in mind today, as we start talking about moving things to make the process of contraction happen, we are using gated channels that are not always open. When I open things, they're always going to move them from high concentration to low concentration. That's what brings us to our last set of questions here. Everybody's favorite salty banana. This should be old hat, right? We know our salty banana. Here, let's draw the salty banana, because why not, right? Here's my banana, and that banana has some salt. I guess I should put the salt on the outside, right? There's my salty banana, salt on the outside. Because it is a banana, what does it have a lot of inside of it? What's inside this banana? Yep, whole lot of K plus potassium, whole lot of potassium. It's a salty banana. What do we have a lot of on the outside? It's a salty banana. Yep, the one that we're caring about today is sodium. What's the other one that's out there? Even though we don't care about it today. We'll care about it next week with the neurons. It's important with neurons. Yeah, there we go. My other one that lives out there, chloride, Cl minus. Remember, salt is NaCl. Both of those, I've got a bunch on the outside. K plus is potassium. I've got a lot of that on the inside. So we're using gated channels. If I use a gated channel for sodium and I open it up, which way does sodium want to go? Where's sodium going? Yeah, sodium wants to go in, right? Because there's a bunch outside, so it wants to go where there's less. Sodium is going to go into the cell. Okay. I open up a channel for potassium. I've got a lot of potassium inside. Yeah, so potassium is going to want to go outside, out of the cell. This last one here wasn't on our salty banana, which is why I told you that you had to do a little bit of digging in your lesson outlines. When I open up a gated channel for calcium, which way did our pictures show us that calcium goes? How does calcium move when I open up a channel for it? Can we tell? Yeah, so calcium is going to go into the cell, And this is going to be something that we see best when we're looking at the way that neurons work. We'll see it I'll show you, I think I have a picture in your lesson outline that shows us this. We have more calcium outside than we have inside, and that's actually on purpose. because I really strictly control the amount of calcium that's floating around in my cytoplasm, or in the case, since it's a muscle cell, inside my sarcoplasm. Because calcium, we talked about last week, calcium likes to go and attach to a protein and make that protein change its shape. Which of those proteins from class last week does calcium like to attach to? Do we remember its name? The protein that calcium attaches to. Protein that calcium, I'm just going to say binds because that's shorter. Yeah, exactly. The name of that protein is troponin. Remember, troponin is my push pin. The push pin helps to hold that wet spaghetti noodle protein called tropomyosin in place. If tropomyosin is in place, no muscle contraction can happen. So if I have too much calcium floating around inside my muscle cell, what's going to happen is it's always going to deactivate troponin. Troponin is never going to hold tropomyosin in place, and my muscle cell will constantly be contracting, all because I've got too much calcium on the inside. So when we're thinking about the movement of calcium, calcium is very strictly controlled, low concentrations inside the cell, which means if I open up a channel for it, it's going to want to come inside. There's not a lot inside, let's make it happen. So the 3 ions we're going to talk about today: sodium, which wants to go into a cell, potassium, which is going to shoot out of a cell, and calcium that would also want to come into the cell. So quick overview of some stuff to give us groundwork for what we're going to talk about today. Let me pull up our overview picture slide here, and I'll have you tell me what page we're on. What page do we have this on? Okay, Christina's saying page 10. Okay, so let's talk about what this picture as a whole shows us. This picture as a whole is showing us what's called excitation-contraction coupling. Excitation-contraction coupling. And that's what I told you we were going to spend our class time today talking about. Now, this name sounds super scary, but we're going to break it down so that it's not actually that scary. Let's start with this last part of its name, or I guess middle part, technically. This middle part of its name is contraction. When we talk about contraction in the name of this process that we're looking at here, what we're actually talking about is what we did in class last week. Last week, we talked about the thing called the cross-bridge cycle. The cross-bridge cycle, remember, was those set of 4 steps that allowed myosin to attach to actin and then move actin to contract my muscles to make them smaller. So when I look at this name here, excitation-contraction coupling, contraction is referring to the cross-bridge cycle, the way that I actually contract my muscles. Excitation, when we have that word in its name, excitation, can't spell it, there we go. Excitation is referring to the excitable cells called neurons. So when I say a cell is excitable, what that means is I can change its charge. Neurons can change their charge. Muscle cells can change their charge too. So when I'm looking at this word excitation in the name of this process, you should be thinking neurons sending a message. So excitation, neurons send a message. Contraction, that's the cross-bridge cycle. That's the muscle contracting. Coupling just means we put those 2 things together. So we'll add that note here, coupling. The 2 processes happen together. Excitation-contraction coupling. All it means, neuron sends a message. When that message is received by a muscle, it contracts. It does a cross-bridge cycle. Contraction and messages, they're coupled together. I've got to have both of them. During our class last week, we talked about the contraction side of things. We talked about how myosin and actin interact with each other. Remember, for myosin and actin to be able to interact with each other, we said just a moment ago that we've got to lose this push pin. Troponin has to pop out of place to allow the wet spaghetti noodle, that's tropomyosin, to slide out of the way, to let myosin attach to actin. So when we're thinking about kind of the ultimate goal of how a neuron is going to make a muscle cell contract, what that neuron has to do ultimately is it's got to help us get this push pin out of the way. Or put another way, it's got to help us release calcium that's stored in that organelle we talked about, the sarcoplasmic reticulum. We've got to figure out a way to spit out that calcium from the sarcoplasmic reticulum so that it can go and pop out that push pin. The way we're going to get this sarcoplasmic reticulum to spit out calcium is by changing the charge on the membrane so that it can push open channels for calcium. So I change my membrane charge on a muscle cell so that these voltage sensitive proteins, voltage sensitive meaning charge changes, change me. When voltage sensitive proteins that are here in my T tubules, when they change shape, they push on some mechanically gated calcium channels that I find on the sarcoplasmic reticulum. These mechanically gated channels, they're mechanically gated. How do I get those open if they're mechanically gated? Yeah, mechanically gated channels, I have to push them open. I have to physically change their shape. So my calcium that's hiding inside the sarcoplasmic reticulum, it's got this gate on it that has to be physically pushed open. I got to push it open. The way that I push it open is by changing the shape of some proteins that are here in the T tubule that change their shape when the charge freaks out. So when it gets really positive here in the tubule, these proteins change their shape and they push on my calcium proteins, my calcium release proteins. So if I need my charge to change inside the T tubules, the way that I'm going to get my charge to change, which is going to allow me to push on these channels here, the way I get this charge to change is back at a place that you looked at in lab. The name of the place is called neuromuscular junction. The neuromuscular junction. This is the place where a neuron meets a muscle fiber. This is going to be the place where I first start changing the charge on the plasma membrane. I change the charge right here at the neuromuscular junction. Then I send that change in charge all the way across the membrane, all the way down into the T tubules. Because when I send it down here, it changes some protein shapes and lets me spit out some calcium. So biggest picture overall, neuron sends a message to a muscle cell. That message changes the muscle cell's charge right here at one place. Then we're going to send that charge change. We went from negative to positive. I'm going to send that all across the membrane, all the way down into these things called T tubules, where they're going to allow us to push on channels that spit out calcium. When I spit out that calcium, that makes muscle contraction happen. Let me pause for a moment so we can process a little bit. Do we have any questions that we can articulate right now? You can probably hear my daughter in the background. Apologies. Yeah, so Nicole asked if the charge travels to the T-tubules. Yes, it does. So the first place I change my charge is at the neuromuscular junction, but then I send it all across my sarcolemma, all the way down into those T-tubules. And we can talk about the action potential. I guess that's probably a good place for us to go next. Let me find that picture. So Nicole's asking what opens the mechanical gate. Well, it's mechanically gated, so we said that it had to be pushed on, right? What's going to push on it are these little proteins that are here connected to the T-tubule. Notice how they're listed here as a voltage-sensitive T-tubule protein. There are some proteins that live inside the T-tubule that when the voltage changes, they change their shape. Their shape change presses on these mechanically gated channels that are in the sarcoplasmic reticulum. So what's going to push on them are the proteins that live inside the T-tubule. They change their shape because the membrane charge changed. And when they change their shape, they push open these mechanically gated channels. Let's talk charges. Let's talk about how charges work. This graph is not quite the same as what we looked at in unit number 1, but it's very similar to what we looked at in unit number 1. Remember in unit number 1, we talked about this fancy word here, membrane potential. What was the easy word I told you to put in the place of that word potential? What's the easy word for what potential means? Yeah, so Nicole is right. When we see membrane potential, remember that I told you I want you to think of it as membrane charge. Instead, think of it as membrane charge. I'll put that up above it so we can see it. We are looking at a graph that shows us from when a muscle is not doing anything, when it's at rest, if you will, resting membrane potential, through the process of when muscle contraction is going to happen. This is what happens to a muscle cell's charge when it receives a message telling it that it's time to do the process of muscle contraction. Now, these are some words that we've already heard. We've already seen them in unit number 1. By the way, I'll mention if any of it doesn't quite make sense, check out lesson number 4 again. Go back to your notes packet from lesson number 4. Because we talked about things like depolarization and repolarization. These are the words that we use to describe what's happening to our membrane charge. So we have the resting membrane potential. By the way, I need you to underline, highlight, star in your notes that the resting membrane potential of a muscle fiber is -90. -90. Because what was my number on a neuron? It's different on a neuron. Yeah, neuron number, which we will have to remember because that's where we're going next lesson, -70 millivolts for neurons. Muscle cells start off even more negative than neurons do. Start at -90 millivolts. When a muscle cell gets a message from a neuron telling it that it's time to do the process of muscle contraction, that muscle cell will depolarize its membrane, meaning it'll go from -90 all the way up to +30, just like our neurons did. It goes from negative to positive. But once it hits +30, it realizes I can't stay here. This is not natural. It goes back down and does the process of repolarization to get back to a charge of -90. So resting membrane potential on a muscle cell, -90. That's where I am when I'm not contracting. When I'm doing the process of contraction, I go all the way up to +30, and then I work my way back down. Just like with neurons, when we're talking about the way that we get this process of depolarization to happen, we use chemically gated ion channels. Chemically gated ion channels. Remember, chemically gated means I have a chemical key. When that key attaches to my channel protein, it opens it up, and it either allows stuff to go out of my cell or stuff to go into my cell. So at this time point right here where we start to see the membrane charge go up on a muscle cell, what happened is I had a neuron that talked to me and told me it's time to do muscle contraction. So I received a neurotransmitter, it opened up the chemically gated channel, and look, it's a chemically gated sodium channel. We just talked about this a couple slides back. When we open a channel for sodium, does sodium want to go in or want to go out? Which way does sodium go? Yeah, sodium wants to go in. So sodium comes into my muscle cell. As the sodium comes in, it brings with it its positive charge. Remember, sodium is Na+. Emphasis on my plus right here, Na+. So sodium comes in and brings its positives with it. Plus, 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 we're bringing in positives that raises or depolarizes my membrane charge. Now, at some point, kind of like we saw with our neurons, at some point, it's not just a chemically gated channel that is open. At some point, we also open the kind of channel that opens when charge is funky. What's the name for channels that open when our charge is wrong? What are those ones called? Yeah, so those are the voltage gated channels, absolutely. So we receive a message with a chemically gated channel. Ariel asked the question, would neurotransmitters open up the chemically gated channel? The answer to that is yes, because neurotransmitters are a type of chemical. I send that chemical, it starts to let sodium come inside. We get enough sodium inside that is going to get me all the way up to +30. When I'm at +30, my membrane charge is completely wrong. I'm going to open up a channel for potassium that is also sensitive to membrane charge. So we use voltage-gated potassium channels to bring my charge back down, to do my process called repolarization. Now, when we talk about potassium, where did we say we had a lot of potassium? Inside or outside? Where is there a lot of potassium? Yeah, there's a lot of potassium inside the cell. So when I open a channel for potassium, potassium wants to leave. It wants to spit out. So we spit out potassium, we're losing all of these positive charges. As I spit out my positives, it gets me back negative. It brings me back to my resting membrane potential. So here's what we've said. We said a muscle is doing its normal life thing, nothing's happening, receives a chemical message from a neuron, opens up some chemically gated sodium channels, starts to get positive, opens up those voltage gated sodium channels, gets way positive, bring in a whole bunch of sodium. We got to fix that. Voltage gated potassium channels open up, spit out potassium, bring us back down to normal to allow us to get back to resting membrane potential. On the neuron graph, I think we labeled this last time, this point up here, we said that this is when a neuron talked to its neighbors, when it got all the way up to positive 30. This is when neurons talk to each other. When we're talking about muscle cells, this positive 30 up here, this is the point when a muscle cell contracts. So a muscle cell has to get to positive 30. When a muscle cell gets to positive 30, this part at the top of my graph is when muscle contraction happens. And the reason that's going to be when muscle contraction happens is because this is my voltage or my charge that leads me to spit out that calcium from my sarcoplasmic reticulum. So when you're thinking about this graph, this part up here, when my membrane charge is positive 30, that's when the process of muscle contraction is going to happen for my cell up here at the top. How do we feel about this graph? Thumbs up, thumbs down, or questions? Yeah, so Nicole asked, at positive 30, the calcium is released. That is correct. Yes. So this is the point when I would release the calcium, which, like we talked about last time, is what allows me to do muscle contraction. So this is where I spit out the calcium so that it can attach to troponin, so that it can move tropomyosin, all that jazz. All that cross-bridge cycle stuff starts right here, because this is where I spit out the calcium. Absolutely. Okay, so let's take this process where I go from receiving a message, freaking out my membrane charge, and bringing it back down. Let's consider, let me go back one. Let's consider how that graph we just looked at is what's happening right here. I've received a neurotransmitter, so I bring in a bunch of sodium, and that gets my membrane charge right here all the way up to positive 30. Okay, that's great. I spit out some calcium right here, and this little tiny part of my muscle cell can contract. Awesome. Except not really awesome, because this part needs to contract, and this is a really long cell that goes all the way down here. I need this part to contract too. When a muscle receives a message at the neuromuscular junction, I can't just change the membrane charge right here, because that would mean only this part of my muscle cell actually contracts. I need everywhere to contract, and the way that I'm going to do that is by using something called an action potential. An action potential. Can you tell me what page we're on? Are we still on page 10? Or did we move on? Action potential. Okay, we're on page 9. Okay. Action potential still has that word potential in it. Let's see if we remember now. What does potential mean again? What's that word potential? Yeah, potential still equals charge. Okay, potential still means charge. When you see that word action, I want you to think moving. An action potential is when my membrane charge changes, and it changes everywhere. It's moving. So here we're looking at the plasma membrane of my muscle cell. So over here, I'm going to type it because I'm not going to, my drawing is going to look terrible if I try. Over here on the left, we've got the neuromuscular junction. The neuromuscular junction. So the place where the neuron met the muscle cell, that's over here. So I change my membrane charge right here. Here's what happens. Chemically gated channels for sodium open up. They bring in my sodium with its positive charge. The inside of my muscle cell at this special location becomes positive 30. That's what we just looked at on the graph. But with my muscle cell membranes, with my sarcolemma, we have voltage sensitive channels or voltage gated channels that are found all across that membrane. So voltage gated sodium channels that are found right here. So at my neuromuscular junction, where a chemically gated sodium channel opened up and let in a bunch of sodium and made this part of my membrane positive 30, the neighboring part of the membrane says, oh, we're going positive here. I'm a voltage gated channel and my voltage just changed. So what happens then is my voltage gated sodium channels that live in this part of the membrane next door, they open up too. So you can see them here, they're open right here. My voltage gated sodium channels right here opened up, which made this part of my membrane go positive now because I brought in all my positive charges. Well, the next door neighbor part of the membrane also has voltage gated sodium channels. When this part of the membrane goes to positive 30, then this part of the membrane says, oh, we're going positive, I'm going to open up. And my voltage gated sodium channels next door open up. So far what we've seen on the membrane, I let in some sodium at the beginning because my chemicals, my neurotransmitters, opened up sodium channels. That led my neighboring sections of the membrane with their voltage gated sodium channels to open up sodium in. I have depolarized my membrane from beginning to almost the end. This would keep going if we could do this forever, right? So we could open up the ones right here and the ones that are over here. Voltage gated sodium channels are everywhere on the sarcolemma, and they're voltage gated. So when the charge changes, they open up. So the first part of an action potential, let's make some notes for ourselves. Thing number one that happens, number one, chemical attaches to chemically gated sodium channel, sodium. When a chemical attaches to the chemically gated channels, sodium comes in and we depolarize the membrane. Here's kind of step one of what happens. This is the stuff that happens at the neuromuscular junction. When that stuff happens, then what happens is voltage gated sodium channels open. Voltage gated. They open up because the membrane was depolarized. So voltage gated sodium channels open. That depolarizes, so we'll add our note again. New membrane section depolarizes. The next little set of part of my membrane is also going positive. That's going to cause the neighboring voltage gated sodium channels there to open up. So we could do one of those things. I don't know quite how we draw it. I guess kind of do arrows back and forth, right? This goes all the way down my membrane. Voltage gated sodium channels open in one place, which depolarizes the membrane, which makes more voltage gated sodium channels open, which depolarizes that section of the membrane. And we just do this all the way across the membrane. Notice though, and we saw this on the graph, I don't just want my membrane to go positive. I don't want to stay positive. Positive is not good for me. Let's see if we remember. What's the normal charge on the plasma membrane of a muscle fiber? What's its normal charge? Yeah, so we're remembering normal charge for a muscle fiber is -90. Right now, at this section of my membrane with all that sodium inside, is at positive 30. Muscle fiber says that's a no-go. We are not staying at positive 30. So what happens next, my next step in the process of an action potential, is voltage-gated potassium channels open. Voltage-gated potassium channels are going to allow my cell to spit out potassium. See how I'm spitting out potassium here? Because potassium has a positive charge. If I spit it out of my cell, it's going to make the inside more negative again. What we're seeing here in green is the process of repolarization. Blue shows me depolarization, where I'm going positive. Green shows me repolarization, where I'm trying to get back to normal, trying to get back to negative 90. See, this part right here is where my membrane has gone back to negative 90 millivolts. Back here at red, I'm at resting membrane potential. That's normal. So first I bring in sodium. Sodium depolarizes the membrane. When I'm completely depolarized, I'm going to use potassium to help me repolarize, the goal being to get back to negative 90. Now, while this section was positive, the neighboring section went positive. But when it got all the way to positive 30, notice that this section then opened up those voltage-gated potassium channels to repolarize itself as well. But remember, when this section was positive, it caused this section to depolarize, and that opened up the sodium channels. So yeah, kind of like Nicole described, think about it like a ripple effect. You drop a rock into water, and we change the membrane charge, or we ripple everything across that membrane. So first I messed up this charge, then I mess up here, then I mess up here, then I mess up here, all the way across the membrane. It's an action potential. It's a moving change in charge. So we change one place, we change the neuromuscular junction. That's going to allow us to change the entire membrane. It's going to take that membrane charge elsewhere across the membrane. Let me just add, for the sake of clarity, our step 6 here is membrane repolarizes. That's the function of potassium, right? Is to repolarize the membrane. Once I'm repolarized, I am ready to get my next set of information. So I repolarize my membrane to do this contraction process all over again. This is an important idea that it's really important you understand, not just memorize. So I need you to help me. What parts of this are tripping us up, or what questions do we have at the moment? Do we have some mind blown emojis going on here? Action potential. And it's got a frog. I like it. Christina's got her nerd glasses on. I like that too. Okay, well, let me see. I want to give us a little more context. Yeah, that's totally fair, Ariel. Soaking it all in. Let me give you some context. Imagine this right here. So we're seeing the membrane, right? We're seeing the membrane, and we depolarized it, and then we repolarized it. We moved our membrane charge everywhere. Let's go back to this picture. This picture, remember, we had our chemically gated sodium channels right here. But then next to those chemically gated sodium channels over here, we've got those voltage gated channels. So those voltage gated sodium channels open up, and this part gets positive. And then this part gets positive. And this part gets positive. And then this part right here is positive. And then we hit those things called T-tubules. Remember at the beginning, we talked about how T-tubules are places where the membrane folds into the cell. Those T-tubules are covered in voltage-gated sodium channels and these voltage-sensitive tubule proteins. These are the proteins that we said they change their shape when the membrane charge changes. So I've got my sodium channels that are lining inside here. Their job is just to change the charge on the membrane. These voltage-sensitive proteins that I see right here, their job is to freak out and change their shape when the membrane gets positive. Because when they change their shape, they press on the sarcoplasmic reticulum. Remember, the sarcoplasmic reticulum has mechanically gated calcium channels. Mechanically gated calcium channels. They live here on the sarcoplasmic reticulum. When I press on them, because that's what mechanically gated means, when I press on them, they spit out calcium. And that calcium they spit out is going to let me do muscle contraction. So my voltage sensitive proteins here, their job, pushing on my mechanically gated channels. And we got them to change their shape with an action potential. With the membrane charge change that moves all across the membrane from beginning to end. Yeah, so Ariel asked a great question. She said, so just to clarify, all this stuff that we talked about happens before muscle contraction. That is correct. Yes. All of this has to happen correctly for us to get to the place that we talked about last time. So for us to be able to slide actin and myosin past each other, for us to be able to do any of that stuff to help you move, we have to first freak out the membrane charge everywhere. And the way that I freak out the membrane charge everywhere is because I started with these chemically gated channels, listening for those chemicals, those messages from the neuron, and then I turned it into my voltage gated channels that changed or that opened because my charge is changing because of these chemically gated channels. So here's my excitation stuff, right? Remember, we're looking at excitation-contraction coupling. Here's the excitation part of things, where I change the charge. Here's the contraction part of things. So they all fit together like one massive puzzle. This is like a 1,000-piece puzzle, right? Like this is a big picture. Lots of parts that come together. Yeah, ain't that the truth? Just like with the cross-bridge cycle, remember last week I told you talk out the cross-bridge cycle out loud with other people? We need to talk this process out loud with other people. Whether it's people from class, whether it's people from your family, if you can explain what happens in each of these steps, if you can describe the functions of our different types of proteins, that will help you to understand what's going on in the process. Because remember, Dr. Allis loves her processes and she loves her application questions. And if we've got a process happening, you better believe that I can mess up steps in the process. And then I ask you what happens if I mess up those steps. So make sure that we talk this out. Or if you don't like talking to other people about this, you could talk it out to yourself in front of a mirror. Or if you really don't want to talk out loud, go ahead and write it on paper. See if you can explain this process with those types of channels, with the proteins we talked about, with the ions we've talked about. Yeah, no joke, right? Christina's saying, hint, hint, everyone, right? 100%, I promise you, I will ask you questions about how this process works. I know you hate it, but if we know it inside and out, we'll be able to nail those questions. Yeah, Jessie said that she likes to write it. Writing definitely helps. For sure. Yep. And then it gives you something you can study from. And actually, too, good thing with this would be a flow chart. So make yourself a chart that starts with neurotransmitters being spit out by a neuron and ends with the process of muscle contraction. If you can make yourself a flow chart with those steps, I bet you'll be able to answer those application type questions. Yeah, so turn it into a flow chart. See if we can list the order that everything happens in. The other thing I'll talk with us about today, about 15 minutes left today, the other thing I want to talk with us about is briefly what can go wrong with this process. So you're doing two correlations, medical correlations, with the process of excitation-contraction coupling. To help us understand one of them, which is the biochemical warfare agent called sarin gas, we need to talk about something in particular that is called acetylcholine esterase. Acetylcholine esterase. Help me out in the chat. Which page of the lesson outline are we on now? Where do you have this picture? Have we found it yet? Okay, same page 11. Perfect. Okay, so we're on page 11. Let's talk a little bit about acetylcholine esterase. So we know that acetylcholine esterase is an enzyme because it ends with this part right here, ACE. Your enzymes in the body, most of them end with an ACE. And most of my enzymes that end with an ACE gives me an idea of what they do or what they break down. This is not a trick question here. Acetylcholine esterase breaks down something. Can we tell from our picture or from its name? What does acetylcholine esterase break down? Yeah, so acetylcholine esterase breaks down a neurotransmitter called acetylcholine. Yeah, so that's a big long one to write its name, right? So just abbreviate it, ACH, totally fine. Acetylcholine esterase breaks down acetylcholine. Acetylcholine, I didn't, I guess, use its name a lot in our excitation-contraction coupling discussion, but what you should know is that acetylcholine, that's the chemical, that's the neurotransmitter that a neuron uses to talk to a muscle cell. So when a neuron, here's my neuron up here, wants to tell a muscle cell that it's time to contract, the way that it sends that message, the chemical it spits out is acetylcholine. This is my message that says time to do muscle contraction. So when a neuron spits out acetylcholine, here's that acetylcholine, we spit it out. To get my muscle cell to contract, that acetylcholine goes down and attaches to our chemically gated sodium channel. Not a trick question. And it's the same one I keep asking, right? Chemically gated sodium channels. Are they or aren't they always open? Chemically gated. Yeah, not always open or gated. They are chemically gated. So I'll answer this one for you, right? We use chemicals to open them. The particular chemical we're using is this guy up here, acetylcholine. So neuron spits out chemical key, acetylcholine. Acetylcholine, that chemical key comes down and attaches to my chemically gated sodium channel. It opens up, allows some sodium inside. As the sodium gets inside, we generate that action potential, the change in membrane charge that goes all over the place. The thing we just talked about. But here's the deal. Once I open up that chemically gated channel for sodium, I don't want it to stay open forever. I've heard this message, this acetylcholine. I'm doing my muscle contraction. I'm done with acetylcholine. So I have this chemical acetylcholinesterase that its one job in life is to chop up acetylcholine. I've heard that message. I opened up this channel, in came the sodium. Now I want to chop up that message because I don't want it bouncing around forever. I want that message gone. So acetylcholinesterase is a little enzyme, it's a protein in the membrane that chops acetylcholine in half into something called acetate and into something called choline. When I've chopped acetylcholine into these two pieces, I can't open up another chemically gated channel anymore. These two pieces by themselves can't open up the channel. The only thing that can open up the channel is acetylcholine when it's in its whole piece. You see, it goes back to our idea from lesson number 1. Anatomy dictates physiology. I've got to have the right shape to do the right job. The right job is opening up a sodium channel. If I have the wrong shape, I can't do that job anymore. So the goal of acetylcholinesterase is to chop up acetylcholine so that it's in the wrong shape and it won't go and activate another receptor. See, we have in our picture one place for these chemically gated sodium channels. But if we were more realistic or more honest, we would also have, oh, wrong one here. We would also have a receptor right here, and we'd have a receptor right here, and this whole space inside here is covered in these receptors for acetylcholine. Once I've heard that message and it detaches from the receptor that it first bound to, I want acetylcholinesterase to chop it in half so that it can't go and attach to this receptor over here or this one over here. Because every time it attaches to one of these sets of proteins, it's going to cause a muscle contraction. So I attach acetylcholine, in comes the sodium, there goes my action potential, and I'm contracting my cell. Once I contract once, if I chop it in half, it won't make me keep contracting. So the goal of acetylcholinesterase is to break down acetylcholine once I've heard the message. Now, sarin gas is a chemical warfare agent that messes with acetylcholinesterase. For anyone who has had a chance to read about sarin gas, can you tell me in the chat, how does sarin gas affect acetylcholinesterase? Could we tell? Okay, so yeah, Hannah is typing out big picture for us. When we're exposed to sarin gas, it is harder for us to relax. Yep, our muscles stay contracted. Okay, so we're along the right line. Christina's saying there's too much of something. What is there too much of when we're exposed to sarin gas? When Hannah's talking about our muscles contracting, yeah, our muscles contract every time we have acetylcholine that's present. When we're exposed to sarin gas attaches to this enzyme, acetylcholinesterase, and it prevents acetylcholinesterase from doing its job. So remember, acetylcholinesterase is supposed to chop up this message that says to contract. If I block acetylcholinesterase, I can't chop up this message. So this message came from the neuron once. My muscle was supposed to contract once, except I'm not chopping it up after I heard it. It's floating around. And now it's going to a neighboring chemically gated sodium channel, and it's causing that one to open, and it's making me contract again. And I still can't chop it up with acetylcholinesterase, so it comes over to this channel over here and opens this one, and I contract again. When we are exposed to sarin gas, my enzyme that's supposed to chop up the acetylcholine message when I'm done hearing it, it doesn't chop up that message anymore. And I just keep hearing it over and over and over again. I'm responding to the message to contract that a neuron sent 5 minutes ago. I'm still responding to that same message. Plus, I'm responding to any new messages that it sends me. So when a person is exposed to sarin gas, and you're going to read a little bit more about it, sarin gas can be deadly. What happens with it is I can no longer break down acetylcholine, and I keep contracting and contracting and contracting. Usually what makes this gas deadly is respiratory failure. So our respiratory system is so constantly contracting that the muscles essentially just die. So very sad correlation to make, but I think it's important that we understand sarin gas is an agent that's actually been banned worldwide because it's just considered cruel and unusual punishment. It's a chemical warfare agent that as a world we've decided is not okay to use. So little, but a good correlation to make. If I can't use acetylcholine esterase, that's what I see happening with sarin gas. A lighter medical correlation that I'm having you guys make this semester is Botox. So when we talk about Botox, if you go to their website, here's their tagline: own your look. So Botox helps to get rid of things like frown lines, crow's feet, forehead lines, all those kind of things that any of you that have kids home with you right now, we're gaining a lot of these right now, right? we're getting the frown lines and the crow's feet. So the goal of Botox essentially is to make you look younger, right? Or make you look more relaxed. So things like we've got the frown lines up here, or the crow's feet that we can see over here. That's big picture what Botox does. The way that Botox works is we actually, let's go to here. We'll go back to that picture. The way that Botox works is, see this little guy right here, this little black thing? It's called botulinum neurotoxin. So botulinum neurotoxin, or botulinum toxin, that's how Botox got its name. It is literally toxic. This is the most toxic substance known to man. So of course we inject it in our faces, right? That makes sense. So you put this toxin in your face or wherever we're trying to stop these wrinkles. What it does is it goes into your neurons, and then it acts kind of like a pair of scissors. So the botulinum toxin does two things. The first thing it does is it messes with these little proteins that you see over here. Now, I promise you on the exam, I am not going to ask you to know the specific names of these proteins down here. So syntaxin and SNAP25, don't learn their names. But what you should learn is that these are the special proteins that are in the plasma membrane of a neuron that the neuron is going to use to help it spit out acetylcholine. So first thing that the Botox toxin does is it goes in and it chops up these proteins right here that help a neuron to spit out neurotransmitters. The second thing that it does, though, is it goes after the other proteins that a neuron uses to spit out acetylcholine. See, we store acetylcholine inside, you looked at it on a lab model actually, inside the synaptic terminal. So remember our model from lab that looked a lot like this? We store our neurotransmitters in little bubbles called vesicles. So my vesicles have this little tail, kind of like an anchor. This protein has to attach to the proteins in the membrane. When this little anchor or tail protein on my bubble with neurotransmitters, when it attaches to this protein kind of reels it in and allows it to spit out acetylcholine. So my botulinum toxin chops up the places on the membrane that would do the reeling, and while it's at it, it chops up the places here, that little anchor or that tail that was being used to pull the vesicle toward the membrane. So what ends up happening when a person gets Botox is I can no longer attach these little bubbles with neurotransmitters to my membrane down here. I've got to attach that bubble to be able to spit out the neurotransmitters. When a person has Botox, we just stop spitting out neurotransmitters because all these little bubbles that are filled with them are not able to attach to the membrane and spit them out. So Botox is not an issue with acetylcholinesterase. Botox is an issue with acetylcholine. I don't spit out acetylcholine at all because these little bubbles that are storing it have no way of spitting it out across the membrane. So two issues that we can see with the process of muscle contraction. Either my acetylcholine stays around way too long and gives me way too much contraction, or I have zero acetylcholine and I can't do any muscle contraction. Now, to be fair, when your muscles aren't contracting, your skin is on top of it is a lot more rested, right? It's a lot more relaxed because there's no muscles underneath that can contract to make it bunch up. But it also means we can't really move this part of our forehead. So I hope you weren't trying to make that face, right? I'll call it the resting face, right? Hopefully you don't want to make your resting face because you won't be able to. These guys can't receive messages here. So you made your face look more smooth. You lose some of your facial expressions, but I guess to each their own, right? Whatever you want to have. So here, let me see. Here's what I'm gonna end with here. Our end of our class today. I had to have a little bit of fun, right? We're talking about Botox. So treating face wrinkles with deadly bacterial toxins. I too like to live dangerously. That's Botox for you in a nutshell. Let's use those bacterial toxins so that we don't have wrinkles. It's totally worth it. Jacqueline asked about lip injections. Lip injections are different because lip injections we're putting some stuff in as opposed to just putting in a tiny amount of toxin. When you get it's called filler. Here's my dermatology background talking here. So you actually are putting in some of the same kind of stuff that you have in your extracellular matrix. So some of those proteins and lipids that you have in normal places in your body, you're adding extra ones. So a lot of times if you're getting filler, you're probably also getting Botox. That's just usually if you do one, you're probably doing the other. So it's not quite the same. If you're getting a lip injection, you're actually literally putting a bunch of stuff in to make your lips look fuller. Theoretically, they should still move unless you put in way too much stuff, and then maybe they wouldn't move anymore. Yeah, Jessie says she's proud of her wrinkles. She's earned them. Yeah, I look at pictures of myself from 10 years ago when I didn't have any wrinkles left, and it's like, I have my wrinkles now, but I earned them. You're absolutely right. And we're all earning our pandemic wrinkles, right? All right, well, that's all I've got for today. We will do a little bit of review tomorrow morning of this stuff, so please be thinking about questions you have about excitation-contraction coupling or about Botox or sarin gas to bring tomorrow. And then the big thing we're going to focus on tomorrow too is talking about those different kinds of muscle fibers. So the glycolytic ones, the oxidative ones, the slow ones, and the fast ones. So that's our stuff that we'll be covering tomorrow. And like I said, bring any questions. We'll definitely take some time to review that. So have a great evening. I look forward to hopefully seeing several of you tomorrow morning at 9:30.